All right, hello everybody and welcome back to the Texas Financial Bureau's educational modules. My name is Matthew Moskal. In the last video, we talked about what moment generating functions are, how to derive some of them, and how to derive the moment generating functions of other random variables that are of themselves functions of random variables. And we showed this with the binomial. We showed this by establishing the fact that a binomial distribution is simply the sum of a bunch of independent Bernoulli trials. So we can classify the binomial random variable as the sum of a bunch of Bernoulli random variables. And from that, if we know that all the Bernoulli random variables and the Bernoulli trials are independent and identically distributed compared to one another, which means they all carry the same probability, probably doesn't change over time, we can derive the moment generating function of a binomial random variable. Now, as I said in the last video, moment generating functions are functions of random variables whose consecutive derivatives evaluated at 0 give us the consecutive moments of our random variable. This can be very helpful in figuring out the distribution of a random variable from the first moment, that's the expected value. The second moment minus the first moment squared is the variance. And then we can go on and compute even further moments from the continued derivatives, like the skewness and kurtosis. This will tell us how symmetric our distribution is, as well as how big the tail, as well as how heavy or light the tails of the distribution are on it. And so these are some of the important properties of moment generating functions. Another important property of moment generating functions is a theorem I'm about to list right here. I'll write it down and then I'll talk about it. Or it's a property rather than a theorem. So if random variable x has moment generating function mxt, and random variable y has moment generating function my of t, and if mxt equals my of t, then x and y come from the same distribution. Now, let me go explain what this means. As I just mentioned, moment generating functions give the moments. They generate moments of a random variable, hence their name. If you can show that one random variable's moment generating function is equal to another random variable's moment generating function, and these two moment generating functions are equal to one another, that implies their consecutive moments are equal to one another, meaning they have the same mean, they have the same variance, they have the same skewness, same kurtosis, and so on of other statistical measures of distributions. If you can show this is the case, then that will say that because all their moments are equal to one another, they come from the same distribution. Whereas if one's expected value was A, another one's was B, and then they had different variances as well, this would imply that they probably come from different distributions. But if you can show the moment generating functions are equal to one another, this will imply the moments are equal, and thus that they come from the same distribution. And so what we're going to try to show, or rather just illustrate, is that the binomial moment generating function actually approaches the normal moment generating function, of which we derived in the previous video. So let me go ahead and recall those moment varying functions for you. So recall the binomial MGF we'll denote it m sub y t is equal to 1 minus p plus p e to the t to the n. The normal MGF, or the standard normal MGF, mz of t is equal to e to the 1/2 t squared. What we want to show, or rather just illustrate, the proof is a little complex, so I'm not going to show it here. I'm just going to try to get y'all the idea of what I'm trying to do. What we are wanting to do is show that this one, as n goes to infinity, approaches this moment varying function. So what I mean is that the idea of it is that the limit as n goes to infinity of 1 minus p plus p e to the t n will equal 1/2 t squared. And thus what this is implying is as we increase our sample size, or in the case of decision trees that we talked about in the previous week, as we increase our periods in our decision tree, we actually approach the normal distribution. And this is very important because what it means is that decision trees, they're discrete, and binomial is a discrete distribution. So I'll say comes from discrete comes from continuous. So as we increase the number of periods, our binomial distribution, a discrete distribution, actually will be able to be approximated. And I should probably say that instead. Is approximately. It can be approximated by a normal continuous one. And I'll put up a visual which I think will really help illustrate this fact. And let me also put the title of this video, the normal approximation to binomial. So let me go ahead and put up a visual of this. So first, recall how a decision tree looks. It has an up node, down node, and so on, and it's meant to illustrate how our stock price moves throughout a certain period, throughout the certain life of a contract, of an option contract. Usually is why we create decision trees, because we want to estimate, or we want to find the fair value of an option by looking at how its stock price moves throughout time with some probabilities. So let me show you in a 2-period tree. So 2-period tree, we have this, where S initial is right here, then it goes up, or up, down, up, down. And this is all, we'll say this is 1 year or just T. This will be, say we have an option contract over that is last 1 year. Each of these would be 6 months, where we would see what the stock price is at the end of 6 months. We can take this further and maybe get even more precise. That's ugly. By doing a 5-period tree, which would be that's 2 periods, 3 3 periods, 4 periods, and then 5 periods. Keep in mind, this is still 1 year. And then this is still the same time frame, but now we have made more periods at which we will check what the stock price is and how it's shifted. So as opposed to being 6 months, let me do a 6 period tree. As opposed to being 6 months apart, just for 2 periods, we check it at 6 months and we check it at a year. In a 6 period tree, we would check it every 2 months. So this would be 2, this would be 2, 4, 6, 8, 10, 12. And we would check it at all of those time frames. So we're getting a little bit more precise in how the stock price shifts. But if we were to go to, let's say, a 20 period tree, I'm not going to draw the full thing, but I just want y'all to get the picture. And then we keep going. We'd have something like that. And then where this is S initial, and this is still 1 year or an expiry time of T. So now we're getting even more precise. We're now checking the stock price at every 12 divided by 20, 6/10, a little over every half of the month. So probably about, like, I'd say in between 2 to 3 weeks, we're checking the stock price. And we do that over the whole year. So we're getting more and more precise. As we were to take this to infinity, and as well, in this final thing, we're allowing a much wider range of values. See, in here, we have only 3 values at which we can check. And here we have 1, 2, 3, 4, 5, 6, 7 values. And then here we have 21 values of the ending stock price. So as we keep going further in the periods we allow our stock price to take on a much larger and infinite set of values. While they are discrete, when we do this, we can then approximate them in a continuous case. Because discrete is just a finite set of values, but continuous is an infinite set of values at which you can check. And so we can end up approximating these probabilities, whether it's above or below some price, but with a continuous random variable. And that's where the normal random variable comes in. And you can look that this can start to form a bell curve where most of the stock prices are in this big chunk right here, because that's where they have the most chance to go. If you want to be all the way on this extreme, you have to go all the way up, or here all the way down. But if you want to be in this mass, this middle area, there's so many paths you can do. You can go up, 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 down, 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 up, down, up, down, up, down, so on. You get the point. This is what I'm trying to mean. And even further is that the reason we get to the continuous case is because as you increase these periods, this size gets smaller. See, here it's 6 months, here it's 2 months, then here it's like between 2 and 3 weeks we're doing it. So as you shrink this period, the rate at which you're compounding in your interest is also becoming faster as well. Instead of compounding every 6 months and 2 months, you're now compounding every 2 to 3 weeks. Extend that idea all the way to infinity, you'll be compounding every single day. And so this is the idea and of how our interest rates in our period approach a continuously compounded and continuous normal case. And I'm going to mathematically try to show that idea. So pretty much what I'm saying is, let me get a new marker. What I'm saying is, as n goes to infinity, the change in time goes to 0, where this part is change in t, this part is change in t, this part is change in t, and so on. We end up shrinking that time. So yeah, like I said, we could be checking it every single day. 6 months, the change in t would be 1/2 of the whole year. Every day would be 1/365, and so it keeps getting smaller and smaller and smaller. That's what I mean by the change in t going to 0. And so yeah, as the n goes to infinity, change in time goes to 0. More possible stock prices and paths are allowed to be taken on, and our interest rates approach continuously compounded rates. This is the point I'm trying to make, and I will show y'all the idea of it as well. In Austin, I believe I showed y'all it in the continuous compounded videos. But what it means is that the limit as n goes to infinity of 1 plus I to the n to the nt, all this is our stock price, is our interest accumulation for one period. So that would be just from here, that would just be from here to here, this part. But as we do this n times, it goes even further. This will equal, an idea of it is I to the infinity infinity times t, and I compounded many times approaches the force of interest delta. This is what I mean by going from discrete to continuous, and how our rates actually approach an exponential, or how our accumulation approaches an exponential one. And so yeah, and as I just said, by increasing our period size n, we allow our stock prices to take on a much larger range of values, and allow for it to be in this normal setting. Our change in time shrinks between compounding, and thus our interest rates approach the continuously compounded rates. But one of the problems, though, and the reason we don't simply use the normal distribution, is because the normal distribution allows for negative values, and I'll do a visual of that. So in the normal distribution, say our average stock price was 70, and it had some standard deviation, 72, 74, 76, 68, 66, 64, something like that. Notice here, this is fine. Our stock price theoretically could go to infinity. What it can't do is theoretically go to the negative side. Because the normal distribution allows for us to have a probability for negative values, it is not an accurate model to use when it comes to distributing stock prices. And so for this, we take the log and we use the log normal model. When you take the log of any variable, that gets rid of the possibility for negative prices. So for example, you could have like a regression thing with log. And this essentially says the log y pretty much says e to what power gives me y. And notice that e to the power to any power will never be less than 0. Even if you were to say e to the negative infinity, that's just 1 over e to the infinity, which is 1 over e to the infinity, which is just 1 over, I'll call it big number, which is approximately 0, but it will never be less than 0 because nothing in here is negative. 1 is positive, e to the infinity is positive. So this is why we take the log. Because we don't want to allow the possibility for a stock price to take on negative values. And so this wraps up the discussion. This is what I wanted to get across of the normal approximation to the binomial. We talked about how if the moment generating function of one random variable is equal to the moment generating function of another random variable, and those two MGFs are equal, then all of their moments from then on are equal, and thus we can say that they come from the same distribution. We then talked about okay, is there a way we can show the binomial MGF approaches the normal MGF? Mathematically, we can. The proof is a little complicated though, but I just want y'all to have that in y'all's head. Mathematically, we can do it, but it involves Taylor expansion, exponentiating, standardizing, and so on. And so that's why I didn't include it here. And so we can show that the binomial distribution approaches the normal one. Visually, we showed that as well when we showed the decision trees for 2 period, 5 period, 20 period, and then kind of trying to extend that idea where even though our contract time is staying the same, those periods at which we're compounding and seeing the stock price move up and down, it's forming a continuous case. Yeah, it's forming a continuous case where the stock prices are changing continuously each and every day or each and every hour, and so on, such like in the real world. That's the model we're trying to build here. And thus our interest rates approach the force of interest and continuously compounded rates. The reason we cannot use the normal model is simply the normal model is because we can't allow for the possibility of a stock price to be negative, because that just isn't representative of the real world. And so we take the log of it, and we show that this is always greater than 0. And so that wraps up the video. In the next video, we're gonna introduce the log normal model and show stuff about the expected stock price, the variation of the stock price, as well as some probabilities the stock price is up or below some threshold, particularly the strike price, which is important if you're wanting to know the probability for a call. If the probability of the stock price is above the strike price, that would be the probability you're able to make a payoff, or you're able to get something. And then for a put, the probability of the stock price is below the strike price, that would be the probability to make a payoff in a put. And so we're going to derive those and show you how the log normal model is useful. in getting some statistics or some quantitative measures about stock prices. Thank you.